Good evening, everyone. My name is Anshu Joon, from BSc Chemistry Honors Final Year. Today we will read the chapter Synthetic Dyes. Introduction. In our day to day life, we come across many substances which have specific colors. In this unit, we shall discuss what is color, how it is related to the constitution of the molecule, what type of color substance called dyes are currently being used to color various articles of our daily use. 8.2 Color and Constitution. Color. When white light 400 to 750 nanometer falls on a substance, three processes may occur. First, if the light is totally reflected, the substance appears white. Second, if the light is totally absorbed, the substance appears black. Third, if a certain proportion of the light is absorbed and the rest is reflected, the substance had the color of the reflected light. If only a single band is absorbed, the substance has the complementary color of the absorbed band. If a substance absorbs all visible light except one band which it reflects, the substance will have the color of the reflected band. For example, it is evident from the above table that if a substance absorbs blue color, it will appear yellow, which is the complementary color of blue. In fact, no substance absorbs a single band, and hence no dye has a pure shade. For example, malachite green predominantly reflects green light, but also to small extent it also reflects red, blue, and violet light. It may, however, be noted that substances which appear to be colorless also have absorption spectra. In such cases, absorption takes place in the infrared or ultraviolet region, but now in the visible region of the electromagnetic spectrum. Relation between color and constitution. Many theories have been put forward from time to time to correlate color with the molecule structure. Some of these are described below. First, Witt's theory. In 1876, it was observed by Otto Witt, a German chemist, that the intrinsic color of any compound is due to the presence of certain group containing multiple bonds. These groups which impart any compound is due to the presence of a certain group containing multiple bonds. These groups which impart color to a particular compound are called chromophores. For Greek, chroma means color and phorus means pairing. And the compound containing the chromophoric group is called chromogen. Some of the important chromophores are nitroso, carbonyl, ethylenic bond, acetylenic bond, and benzene ring. Further, greater the number of such chromosomes, deeper is the color. This is particularly marked when the chromophores are in conjugation with one another. For example, first, as the number of conjugated double bonds increases, the color of the diphenyls deepens. Second, ethylene 1,3-butadiene and 1,3,5-hexatriene are colorless, but beta carotene, the pigment present in carrots, has orange red color due to the presence of the 11 conjugated double bonds. Oxochromes. Witt also observed that there are certain groups which themselves are not chromophores but deepen the color when introduced into a colored molecule. Such groups are called oxochromes. For example, OH, NH2, NHR, NR2X, that is ClBr or I, CO2H, etc. Even alkyl group exert weak oxochromic effect. Let us now examine the effect of oxochrome on the intensity of color. Both naphthalene and naphthalol are colorless. 1,3-dinitronaphthalene is pale yellow, but 2,4-dinitro-1-naphthol, the dye matrix yellow, is orange red. The presence of oxochrome, that is OH group, has deepened the color, 1,3-dinitronaphthalene chromophore from pale yellow to orange red in Martius yellow. Two other terms which are commonly used in connection with dyes are bathochromic and hypsochromic group. Whereas bathochromic group bring about the deepening, hypsochromic group bring about the lightening of the color. In dyeing industry, deepening of color means color change from yellow to orange, red, purple, blue, green, black. This is exactly the order of the complementary color of the colored absorbed. Thus, when we say that the color of one of the complementary color of the other, it simply means the wavelength of the maximum absorption of the former is longer than that of the later. Since visible color is complementary color of the absorbed band, bathochromic group cause red shift while hypsochromic group cause blue shift, etc. Second, modern theories of electronic theory of color. Two electronic theories have been proposed to explain the origin of color. These are valence bond theory and molecular orbital theory. The most important difference between valence bond and molecular orbital theory is that in the valence bond theory, electrons are dealt in pairs, but in molecular orbital theory, they are dealt singly. First, valence bond theory. According to valence bond theory, the electron pair of a molecule in the ground state are in a state of oscillation when placed in the path of a beam of light. They absorb a photon of appropriate energy and get excited. The wavelength of the photon of the light absorbed depends upon the energy difference between the ground and the excited state. The smaller is the difference, longer is the wavelength of light absorbed. To illustrate valence bond theory of color, let us first consider a molecule of ethylene which may be regarded as a resonance hybrid of the following two structures 1 and 2. To a first approximation, ground state is represented predominantly by structure 1, while excited state is represented by structure 2. The energy state difference between these two states is very large and hence photon of a short wavelength is absorbed. In general, it has been shown that first, a resonance among charged structure lowers the energy of both the ground as well as excited state. Second, charged structures, however, stabilize the excited state more than they do the ground state. Third, larger the number of electrons involved in resonance, smaller is the energy difference between the ground and the excited state. From the above discussion, it follows that more extended the conjugation in a molecule, greater is the contribution of a charged structure. Smaller is the energy difference between the ground and the excited state. Hence the longer is the wavelength of absorption. When this wavelength of absorption is long enough to lie in the visible region, we observe color. For example, ethylene colorless wavelength maximum 175 nanometers, 1,3-butadiene colorless lambda max 217 nanometer, 1,3,5 hexatriene colorless lambda max 258 nanometer, 110 diphenyl 13579 decapentane color orange lambda max 424 nanometer. It may, however, be remembered that the color of the compound is actually the complementary color of the light absorbed. Further, the presence of the both electron donating group, that is group with plus I plus R effect, or the electron withdrawing group, that is group with minus I minus R effect at the end of the conjugated system, will extend the conjugation by involving the lone pair of electron present in the heteroatom with the pi electron on the conjugated system, and will increase the contribution of the charged structure toward the resonance hybrid. Consequently, the wavelength of the light absorbed becomes longer, and when this wavelength lies in the visible region, the compound appeared colored. For example, benzene colorless 204 nanometer, aniline colorless 230 nanometer, nitrobenzene colorless 270 nanometer. Steric effect and color. We know that resonance is maximum when the system is completely or almost completely planar. If due to steric hindrance resonance is inhibited, the depth of the color will diminish or the compound may even become colorless. Molecular orbital theory. According to MO theory, whenever a molecule absorbs a photon of light, one electron is transferred from bonding or non-bonding orbital to the anti-bonding orbital. Deepens transition in which a bonding sigma electron is excited to an anti-bonding sigma electron is called sigma sigma star transition. In the same way, pi to pi star represents the transition of a bonding pi electron to an anti-bonding pi star orbital. An n pi star transition represents the transition of one electron of a lone pair, that is non-bonding pair of electron, to an anti-bonding pi star orbital. This type of transition occurs in molecules containing double bonds involving hetero atoms. The relative energies of these transitions are pi to pi star is greater than pi to sigma star is greater than n pi star is greater than pi pi star is greater than n sigma star n pi star, sorry. Of all these transitions, only pi pi star and n pi star transition lie in the ordinary UV region 200 to 400 nanometer. Furthermore, pi to pi star transition are much more intense than n to pi star transition and hence are responsible for color. Further, as conjugation increases, absorption due to pi pi star transition gets shifted to a longer wavelength and ultimately to the visible region and hence is responsible for the color as explained below. In ethylene, there are two types of transition, that is sigma sigma star and pi pi star. The longest wavelength band, that is pi to pi star, absorbed at 175 nanometer. Since this band also lies in the ultraviolet region, therefore ethylene is colorless. Butadiene has lambda max at 270 nanometer due to pi pi star transition. Thus, conjugation has shifted the band to lower wavelength but still not into the visible region, and the intensity has greatly increased. This may be explained as follows. A double bond consists of two pi molecular orbitals, one bonding and the other antibonding. But when the two double bonds are brought into conjugation, four MOs are formed. Two of these, that is pi 1 and pi 2, are bonding and are occupied by a pair of electrons, which the other two are antibonding, that is pi 3 star and pi 4 star. Thus, it is clear that the energy of the highest occupied molecular orbital, HOMO, that is pi 2, increases, while that of the lowest unoccupied molecular orbital, LUMO, that is pi 3 star, decreases. As a result, energy level involved pi pi star transition now come closer and hence lesser amount of energy is needed. In other words, the energy gap between pi 2 and pi 3 star orbital in 1,3 butadiene is much lower wavelength 270 nanometer than the ethylene 175 nanometer. Further, since the energy level come closer, their interaction is in the excited state increases and hence E max also goes up. In a similar way, we can show that when the three double bonds are brought into conjugation, the energy gap between the HOMO and LUMO become still smaller and the wavelength of pi pi star absorption band increases. And when it reaches the visible region, color that is complementary will appear in the compound. For example, in the polyenes CH3, CH double bond, CH whole N, CH3. When N is equals to 6, the absorption band occurs in the blue region and so the compound is yellow, complementary color. Similarly, beta carotene, an orange pigment of carrots, Absorbed in the greenish blue region, lambda max 478 nanometer and 422 nanometer. Lambda max is equal to 422 nanometer and hence the color is orange. Now let us consider benzene. It absorbed at 254 nanometer and is therefore colorless. Similarly, naphthalene and anthracene are colorless. As the number of fused rings increases, the position of absorption approaches the visible region. Thus, naphthalene will with four linearly fused rings absorbed in the blue region and hence is yellow, while pentacene, which absorbed orange light, is blue. 8.3 Dyes. A dye is a colored substance which can be applied in a solution or dispersion to a substance such as textile fibers, that is cotton, wool, silk, polyester, nylon, paper, leather, hair, fur, plastic material, wax, a cosmetic base, giving it a colored appearance. Condition which a dye must satisfy. A substance can be used as a dye for the textile only if it satisfies the following condition. First, it must have a suitable color. Second, it must be able to fit itself or capable of being fixed to the fabric from the solution. Third, when fixed, it must be fast to light, resistant to the action of water, soap, detergent, etc. during washing or to the organic solvent during dry cleaning, etc. Nomenclature. The chemical names of the dyes are very complicated and hence trade names are more popular. These trade names often include one or more alphabetical letters and a number. Whereas the number indicates the shade, alphabetical letters refer to the color. For example, G for yellow, German clef is equals to yellow, R for red, German rough is equals to red. Sometimes alphabet may also refer to some specific properties. For example, WE for fast to washing. German is equals to boss chest. Sometimes the letter also stand for intensity of the color. For example, 6B stands for deep purple, close to blue. But sometimes these letters may have entirely different meaning. For example, alizarin blue D. Here D stands for direct, which means it is direct dye for cotton. This was the first part of the chapter dyes. Thank you.